Alright, next up I want to spend a little bit of time talking about the memory layout within a process. In order to talk about that, first I have to talk a little bit about what a process is. So a process is an instance of a running program, a running instance of a program. So if we go ahead and run a program, we have our shell, and we run, I don't know, echo hi, then this is going to run a command called echo with the argument hi, and the program that we're running is a program named echo, and it's going to be a process. The procedure is that we find the executable file for this program somewhere on the disk, and then we're going to create a new process with a new process ID. And by we, I mean the shell here. So the shell is going to create a new process. And then we're going to load up data from the executable file off disk into memory within that process. So each process that is running has an address space. If we run echo 5 times, and if echo were a little bit slower than it is, then we could have multiple echo processes running at the same time. A common example where processes get used in a way that's sort of obvious is that if you use the Google Chrome web browser, it's going to create a separate process for each tab. So every tab is a separate running program, a separate instance of the Chrome program running. Now each one of those tabs has its own memory address space, so they have separate memory, and that's useful from a security perspective. Another example is when I open a bunch of terminal windows, every terminal window that I open is an instance of the program GNOME terminal, and logically those terminal windows are separate, although in practice GNOME is terrible and likes to try to cheat and not have multiple processes, so they may not actually be really multiple processes because programmers want to ruin my examples. In any case, a process is a running instance of a program. So if we have our program, we're gonna start our program foo. We've compiled the program foo, and in that program foo we had some assembly code, we had a text section, we had a data section. When we run it, the operating system and the shell are going to work together to create this new memory address space, and I'm going to go ahead and draw out the memory address space as a big old box. And let's assume that we're running this on a 32-bit Linux machine. If we're running this on a 32-bit Linux machine, then we know with 32-bit machine, that means we have 32-bit registers. With 32-bit registers, that means we have 32-bit pointers, unless we're doing obnoxious stuff to be clever and make things difficult, which we're not. So we have our 32-bit registers, 32-bit pointers, that means that memory addresses are 32 bits, and so the address space for the entire computer goes from 0 to 4G or a little more than 4 billion. When I say 4G, I mean 4 times 2, K would be 10, M would be 20, 2 to the 30, 4 is 2 to the 2, so this is 32, that's 32 bits. So the memory address space for the entire computer is 4 gigs. And the neat thing about processes on a modern operating system, modern processor with a large amount of RAM like this, is the operating system and the processor are actually going to work together to tell every running program that they each have their own memory address space. This is one of those things where why this happens is useful to go back and think a little bit about older computers. If you had a computer back in the day where each program, or you could only run one program at a time, then of course every running program has access to all of memory. So you write programs that assume you have access to all of memory. They're going to do things like always load into the same location in memory because nobody else is running. And then when we move to an operating system that allows multiple programs to run at the same time, for compatibility with those old programs that think they have all of memory, it would be nice to make it so that the programs still think they have all of memory. And so that's what operating systems and processors work together to do. The operating system and the processor use this mechanism called virtual memory to lie to the process and tell it that all of memory belongs to it. So when we're running this program foo, we actually, foo sees an address space all to itself with memory addresses that range from 0 to 4 gigs. If it tried to fill all of it, things would go wrong because this 32-bit machine might be a 486 from 1993 and might have 16 megs of RAM, but it sees a 4 gig address space on a 32-bit system. On a 64-bit system, this would go up to 2 to the 64, which is some really big number. In any case, when we execute this program, we're going to load some stuff into memory. We load our text section, we load our data section, and then once those are loaded into memory, the loading process of executing a program, the loading procedure of executing a program to create a new process, is also going to create 2 more regions in our memory address space. It's going to create a region called the stack, logically near the top of memory, which grows down. And it's going to create another region called the heap, logically near the bottom of memory, which grows up. And if we had a small amount of address space and we had a lot of RAM, then this would work the way you would expect. The stack grows down, the heap grows up. If the total amount of memory that they're using fits, everything is okay. If we use so much memory that the stack and heap hit each other, bad things happen, and that's a real problem that people had in historical machines, of having the stack and heap run into each other. But this layout still gives us the maximum amount of space and the maximum ability to have one program use a lot of stack and another program use a lot of heap. So that is our sort of general picture of what a memory address space looks like. We're going to see this a lot. We're going to talk a little bit more about how to use the stack. We haven't really talked about the heap yet, but for the moment, the heap we use to dynamically allocate memory, and we're going to do that primarily with a function called malloc, which I'll talk about a little bit more later. But there is my favorite picture for the semester to draw. We'll be seeing this again. This is the sort of diagram of the memory address space of a single running process.